Well, thanks everyone for coming. It's almost like an extended group meeting, but on a Monday morning. So welcome to the thesis defense of Ashwin Atre. This is kind of a big deal for me and our group because Ashwin is the first student from our group to be defending his thesis. By way of introduction, hopefully I'll get things right, Ashwin grew up in Southern California and then moved to Princeton to get a bachelor's degree in chemical engineering. He graduated from Princeton in 2009 and then came to Stanford in the fall of 2009 to join our material science PhD program. Later on that fall, Ashwin sent me an email expressing interest in joining our group, and I was able to dig up that email. I'd like to read some excerpts to you.
Somehow I knew this was going to happen.
Yeah. Professor Dionne, my name is Ashwin, and I am one of the material science PhD students that attended your presentation. I was awarded a Stanford Graduate Fellowship. This is my favorite part. And I'm hoping that this helps demonstrate my potential as a graduate researcher, as well as relieving the burden of taking me on as a student. While it is still early in the selection process, I simply wanted to inform you of my interest because you requested that we do so. Thank you, Ashwin Atre. It was such a burden taking him on, but thankfully he was free those first few years. More seriously, Ashwin would later join me that fall for some experiments at Berkeley, and despite practically nothing working that day, he was so incredibly enthusiastic and upbeat that I couldn't refuse him a position in my group. 5 years later, and many successful projects, it's incredibly exciting to be here with Ashwin. And I guess before handing over the stage, I just wanted to highlight some of Ashwin's pioneering work that has led us here. First of all, in 2011, Ashwin was working really hard in our lab installing equipment and decided to reintroduce a fashion trend to Stanford, the headband sweatband. In 2012, one of Ashwin's papers was ranked in the top 10% of all-time downloaded papers from the Journal of Optics. That was actually on this day in 2012, so 3 years earlier. And then on this day in 2013, you began the nano-optical tomography work, which will soon be published in Nature Nanotechnology. Of course, you're defending your thesis today, a 45-minute presentation that represents 5 years of incredibly hard work and scientific accomplishment, and I hope you'll enjoy his talk as much as I have enjoyed working with Ashwin.
Well, thank you, Jen, for the amazing introduction, and thank you all for coming to this presentation today. Everyone here is well aware of the importance of light and the fact that the interaction between light and the objects around us essentially define our perception of the world. But something that most people are less familiar with is how these light-matter interactions change when the objects get really, really small. So this is essentially what I'll be talking about throughout my presentation today. But before I get into our own research, I'd like to give you an example of how the ultimate designer, that is evolution of course, has come up with a way to create a brilliant optical response. This is a blue morpho butterfly. Most objects in nature, including the leaf that this butterfly is sitting on, get their color from pigments. Pigments essentially absorb certain energies of light and reflect others, giving rise to the eventual object's color. The blue of this butterfly, however, is not pigmented. In fact, the material that makes up the butterfly's wings is comprised of chitin, a completely transparent polymer. So how is it that a completely colorless material gives rise to such a brilliant blue color? Well, let's zoom in to find out. Using an optical microscope, we can see that the wing is actually composed of hundreds of tiny scales, stacked on top of each other like shingles. If we zoom in another level further, with an electron microscope, we can see that within these scales are hundreds of tiny ridges, and within those ridges are even smaller ridges that have length scales on the order of the wavelength of light, or a few hundred nanometers. It turns out that the interaction of light with these wavelength scale features gives rise to the brilliant optical response that we see here. While this beautiful blue color is surprising and surely useful on some evolutionary level, we as scientists and engineers can actually leverage the unique and often unexpected ways that light interacts with these nanoscale materials to create new optical techniques, explore novel optical phenomenon, and so this is a field that we call nanophotonics. One of the exciting findings of nanophotonics is that nanoparticles, particles whose dimensions are on the order of 1,000 times smaller than the wavelength of light can actually concentrate light into very small volumes. So one of the useful things this could be applied to is in detecting small concentrations of substances. It turns out that in general, a molecule can be identified by the characteristic way in which it scatters light through a process called Raman scattering. However, unfortunately, this process is quite weak, and so if we have a very dilute solution of molecules and we look at the Raman intensity as a function of the Raman scattering energy or Raman shift, we see basically very little signal. Now, if we place these nanoparticles in the solution, they can concentrate the light at the nanoscale. It can increase the interaction of the light with these molecules and therefore yield a larger Raman scattering signal. This process can be so effective, actually, that we can detect single molecules using this particle-enhanced Raman technique. In fact, it was shown that this concentration was so effective recently that they were able to use a simple cell phone camera as the detector to detect single molecule events. Another really practical application that this sort of nanoscale light concentration can be useful for is in photothermal cancer therapy. It turns out that when the light is concentrated to this sort of sub-wavelength scale, it can actually heat up the surrounding material. So here on the left, we see an optical image of gold nanoparticles dispersed on a glass slide, where the dark portions of the optical image correspond to higher concentrations of these nanoparticles. Using a technique called fluorescence polarization anisotropy, these researchers were able to actually probe the temperature, the local temperature, near these nanoparticles and found that the temperature increased by about 7 degrees for the highly concentrated areas of the sample. Most of you are aware that biological cells, including our own, are very sensitive to their local temperature. So it turns out that if we put these nanoparticles inside of a tumor and irradiate them with light, we can actually kill off cancer cells. So here is a pretty disgusting looking mouse where they put nanoparticles into the tumor, illuminated it with light, and after 21 days, the tumor was essentially completely eliminated. And this process is actually currently being fast-tracked for human clinical trials. So while I could go on for hours and hours about all of the different uses that one could find for nanophotonic engineering, I'm going to be focusing on 3 particular applications today. The first is that I'll show you how we can use the rational control of light-matter interactions at the nanoscale to create a metamaterial that operates over a broad spectral bandwidth. Next, I'll show you how we can improve light energy harvesting by utilizing sub-bandgap photons to boost the efficiency of solar cells. And finally, I'll introduce a new technique that we've developed that has allowed us to probe light-matter interactions at the nanoscale and in 3 dimensions. So first, let's start with the broadband metamaterial. To understand a metamaterial, of course, we have to understand how a normal material gets its optical properties. In other words, why does this diamond shine bright like a diamond? So the diamond, as most of you are probably aware, is actually just a bunch of carbon atoms that are arranged in this periodic lattice, where the lattice constant of the particular arrangement of atoms is much smaller than the wavelength of light. So in essence, the carbon or the chemistry of the material as well as its atomic arrangement gives rise to the optical properties. A really useful parameter that we can use to describe how light behaves inside of a material is the material's refractive index. Here we can see that the refractive index depends on both the electric permittivity as well as the magnetic permeability. These 2 quantities essentially describe how the material responds to both the electric field and the magnetic field of light. Unfortunately, most natural materials only really strongly respond to the electric field of light. And so this quite significantly limits the range of refractive indices that is available to us in natural materials. Most natural materials actually have an index greater than 1. So that's where metamaterials comes in. We can actually sort of replace the atoms within a material with meta-atoms that have been specifically designed to respond to both the electric field and the magnetic field of light. In this way, we can affect both the effective electric permittivity and the magnetic permeability of the material, giving us a much larger range of control over the refractive index. So we can achieve positive values, values less than 1, and even values less than 0 with negative indices of refraction. To demonstrate why a fully tunable index would be really interesting, I'm going to describe one particular application, which is invisibility cloaking. You probably have all heard of Harry Potter's invisibility cloak, it turns out that this sort of exotic application is actually not completely unphysical, and we can actually achieve invisibility on a microscale at this time. So in order to describe this, we'll look at a few simulations of how light propagates in the next few panels. So here is light propagating from the top of the screen to the bottom of the screen in free space, and it's completely undisturbed. So you can see the wavefronts propagating undisturbed. Now, if we place an object in this field of view, we can see that the light interacts with the object. It can be absorbed by the object, scattered by the object, resulting in this complex pattern of wavefronts in the nearby vicinity. Now, if we surround the object with a metamaterial cloak, where we've tuned the index to have very particular values at all points of space within the cloak, we can actually force the light to bend around the object and not interact with the object itself. Therefore, the wavefronts outside of this metamaterial cloak actually look like the undisturbed case on the far left. So this application, along with other applications like perfect lensing, really demonstrate why we would want a tunable refractive index, and in fact even be able to achieve indices less than 0, or negative indices. And metamaterials have allowed us to do that. Metamaterials were first proposed as arrays of resonator elements that responded, again, to the electric and the magnetic field of light simultaneously. This the first metamaterial ever created was demonstrated in 2001, and they actually were able to negatively refract light in the microwave frequency regime. Over the years, this same sort of design has been scaled down and augmented a little bit to work in the infrared frequency regime as well as the visible frequency regime, where I'll just draw your attention to the scale bars in these figures, where you can see that the meta-atom or resonator elements of these structures has decreased in size by orders of magnitude over the last decade or so. While these accomplishments are great, it turns out that most resonator-based metamaterials suffer from the same limitation, which is that they only operate over a fairly narrow range of frequencies. So to quantify this bandwidth problem, here I've plotted the bandwidth of negative index operation of these metamaterials as a function of their peak operating wavelength. And we can see that in the near-infrared, we can achieve bandwidths of a few hundred nanometers. However, as we scale down the operational wavelength into the visible, around between 400 and 800 nanometers, say, the bandwidth is reduced quite dramatically. In fact, below 1,000 nanometers, the largest bandwidth reported previously was around 100 nanometers. So if we wanted to make an invisibility cloak or a perfect lens, for example, that operated over the entire visible spectrum, we'd need a bandwidth of a few hundred nanometers in this sort of optical frequency range. So the question becomes, can we rationally design a broadband metamaterial at optical frequencies? And I wouldn't be standing here telling you about this today if the answer was no. So I'll show you how, using the rational control of light-matter interactions, we can actually achieve a bandwidth of a few hundred nanometers in the sort of region, the spectral region below 1,000 nanometers in wavelength. So to gain inspiration for our rational design, we look to the adjacent field of plasmonic waveguides. So here is a schematic illustration of a plasmonic waveguide, which consists of a dielectric channel with two metal layers on top and on bottom. Now, if we shine light at this metal insulator waveguide structure, the oscillating electromagnetic field of the impinging light can actually cause the free charges within the metal surface to oscillate back and forth, resulting in the propagation of a surface plasmon polariton that travels down the channel. In essence, we've been able to squeeze the light from free space into this narrow channel. Now, depending on the materials that we choose for this waveguide, and as well as the thickness or the dimensionality of the waveguide, we can actually get the wave that propagates through this channel to have a negative index of refraction. Back in 2006, Professor Fan showed that such a metal insulator waveguide could be used as a negative index lens, and then a year later, Jen demonstrated experimentally negative refraction at visible frequencies. So what makes these waveguides so interesting? Well, to understand their optical properties, I'll describe a slightly modified version of a waveguide, which is a periodic waveguide. So in this case, we have alternating layers of silver and dielectric material that periodically repeat infinitely in the y direction. And to sort of be able to understand their sort of optical properties, we're going to look at a dispersion curve, which essentially describes how light with different energies behaves in such a structure. So here we're seeing a plot of the free space photon energy as a function of the wave vector, or the momentum of the light within the waveguide. So this waveguide, this infinitely periodic waveguide, supports a positive index mode for all frequencies below the bulk plasmon resonance frequency. This mode is characterized by an anti-symmetric distribution of charges across the metal layers, and because of the way the field is distributed within this mode, it is actually only dominant below the surface plasmon resonance frequency, which I've indicated here with a bolding of that line. The waveguide also supports a negative index mode for all frequencies below the bulk plasmon resonance frequency, and this charge distribution is symmetric across the metal layers. And again, because of the way the fields are distributed within the different materials, this particular mode is only dominant for frequencies between the surface plasmon resonance frequency and the bulk plasmon resonance frequency, which is quite a narrow spectral region. And so what I'd like to show you is how we can transform this structure to change the dominance of these modes so that now we can excite the negative index mode, or the transformed version of this negative index mode, for a larger range of frequencies. So what we're going to do is we use a technique called a conformal transformation. So a conformal transformation that most people are familiar with takes the surface of a sphere or a globe and transforms it into a two-dimensional plane. So this is very useful for map making, of course. The transformation that we're going to use is a little bit more complicated. It takes this infinite periodic stack of silver and dielectric layers and changes it into a metallodielectric crescent. The crescent is composed of a dielectric core with a tapered metallic shell that ends in singular points at the tips of the structure. The reason why we use this particular transformation is that it was previously shown that this metal insulated waveguide to crescent transformation could yield a meta-atom, essentially, that had an extremely broad absorption cross-section. So here, depending on the particular geometry of the crescent that they transformed the structure into, they could get absorption cross-sections that peaked over a broad range of frequencies. So the question is, can we use this transformation to do more than just achieve a broadband absorption? So let's find out what happens to these modes upon transformation. Let's first look at the negative index mode. And upon transformation, we can see that the charge symmetry is preserved. So now the charges that were symmetric across the metal layers are now symmetric about a circle of symmetry. And if we look at the charge distribution as well as a near-field plot of this mode, we can see that it is characterized by a very strong electric dipolar resonance near the tips of the structure, as well as a circulating displacement current through the metal shell, which corresponds to a very strong magnetic moment for this particular mode. If we look at the positive index mode with the antisymmetric charge distribution, again, this charge distribution is preserved upon transformation. And when we look at the near-field plots, we actually see counter-rotating displacement fields indicating a very small net magnetic moment and higher spatial variation of the fields at the tips. When we investigate the differences between these modes, we find that the negative index transformed to negative index mode, shown on the bottom left here, is actually the one that's excited for all frequencies below this surface plasmon resonance frequency. So, and then the other mode is only excited for the frequencies above the surface plasmon resonance. So in essence, we've transformed the negative index waveguide mode into degenerate electric and magnetic dipolar response of this finite meta-atom. One of the sort of caveats of this particular transformation is that, as I mentioned, the tips are actually singular points, which is, of course, not realistic for any real device. And so what we'd like to do is find out whether the same sort of mode characteristics are preserved when we round the tips of the crescent and consider a more practical structure. So as we expect for a finite resonator, we do see resonances appear in a spectrum. In this case, we've calculated the extinction efficiency of the crescent resonator using a finite difference time domain. But if we look at the lowest energy resonance of the structure, we see that it essentially looks identical to the mode that we were exciting in the singular structure. Of course, the field intensity at the tips of the structure are reduced because of these singular points have been rounded out, but in essence, the character of the mode is preserved. Again, we see the dipolar nature as well as the sort of the circulating displacement fields indicating a magnetic dipolar moment. we can more quantitatively describe the resonances of this structure by decomposing the fields scattered by this crescent into their dipolar electric and magnetic contributions. And when we do this, we see that each of these modes throughout visible and near-infrared frequencies is composed of both electric and magnetic character. So in essence, we can use this meta-atom in a metamaterial to control both the electric permittivity and the magnetic permeability of our material. So the only step left is to actually make the metamaterial, in theory, of course, where we put the crescents next to each other and embed the crescents into a dielectric slab. To study their optical properties and measure their index, we use a numerical interferometry technique where we essentially measure the phase of light that has been transmitted through our metamaterial slab and compare that with the phase of light that has been transmitted through free space. Using sort of the difference in these two phases and this relatively simple equation on the left, we can calculate the effective index for this metamaterial slab that we've created. And when we do that, we find that throughout visible and near-infrared frequencies, there are multiple regions where the index drops below 1 and below 0. In fact, within this region below 1,000 nanometers, we see that we have a negative index regime with a 255 nanometer bandwidth, which more than doubles the previous largest bandwidth achieved in this frequency range. So to sort of further characterize and visualize the refractive index properties of this particular metamaterial, we actually perform refraction simulations using a prism. So many of you have probably seen this done in real life, where a beam of light that enters a prism is bent depending on the material that the prism is made of, as well as the sort of angle of the prism. And here, using Snell's law and the angle of refraction through this prism, we can very easily calculate the index of refraction of our metamaterial prism. So in this case, if light bends below the normal, that is positive refraction. And if light bends above the normal, that's characteristic of negative refraction. And if it travels along the normal, that's where the refractive index would be about 0. So here, we essentially make a prism, in theory again, with our crescents. And at a wavelength where we have previously calculated using that interferometric technique a positive index, we see that in fact the waves are bent below the normal, characteristic of a positive index of refraction. And if we actually use Snell's law to calculate that index, it corresponds quite well with our interferometric technique. Now at a wavelength where we expect the light to bend in the other direction or have a negative index of refraction, we do in fact see that that is the case. And again, the index calculated via this sort of visual method corresponds quite well with the phase-based technique. To make sure that this effective index that we've calculated, is not particular to the geometry of the material of the system that we're looking at, we also look at wedges of different angles. And in this case, I'm actually going to just show a wavelength where the index is near 0. And in this case, for both, regardless of the thickness of the wedge or the angle of the wedge, we can see that light propagates along the normal of this wedge, corresponding to that 0 refractive index that we had predicted using the interferometric technique. So to wrap up the first part of my talk, I've showed that we can use conformal transformation to show that the negative index mode of a waveguide is the same modal solution as the electric dipolar and magnetic dipolar response of a finite resonator. And finally, a metamaterial based on this crescent, this transformed crescent, exhibits broadband negative indices spanning the visible and near infrared. So more than just these sort of exotic applications like metamaterial invisibility cloaks or perfect lenses, we can actually also tackle more practical problems like the immediate need for renewable sources of energy, which brings me to my second topic on upconversion enhanced photovoltaics. So this is a pretty famous composite image of the Earth at night. Unfortunately, most of the lights in this image are powered by fossil fuels. But of course, there's a sort of free source of energy that's just waiting to be used, and that is, of course, solar energy. So here I've overlaid a plot of the solar energy that is incident on the Earth, averaged over, I think, a 15-year period, where we can see just how ubiquitous this source of energy is. So what's preventing solar from being used more widespread? Well, it's obviously a complicated problem, but one of the key factors is the cost of solar cells. And one of the key driving the factors that increases the cost of solar cells is their inefficiency. And one major source of this inefficiency is the inability to harvest low energy light. So here is a spectrum of the sunlight as it hits the Earth. And if we're trying to harvest this energy using a single junction solar cell, a conventional solar cell, which is characterized by a valence band and a conduction band separated by a band gap, what happens if we illuminate the solar cell with a photon that has energy greater than the band gap is that that photon can be absorbed by the solar cell and contribute to current. If the photon's energy is less than the band gap, however, it will simply be transmitted through the cell and will be wasted by this conventional solar cell device. So for a single junction solar cell like a silicon cell with a band gap of 1.1 electron volts, it turns out that this wasted energy amounts to about 25% of the energy in sunlight. So the question is, can we make use of these sub-band gap photons to improve solar cell efficiency? One of the ways that we can do this is upconversion. Upconversion takes two lower energy photons and converts it into a higher energy photon. So if we have our solar cell that is transmitting these sub-band gap photons, we can simply place an upconverter behind the solar cell, absorb these lower energy photons, and emit a higher energy photon that can be used by the solar cell back upwards. I should mention that in this design, the upconverter is isolated from the solar cell above it. And so unlike a multi-junction cell, which requires very expensive lattice matching as well as difficult current matching conditions, the upconverter does not require those particular things. Also, in comparison to an intermediate band solar cell, the upconverter doesn't introduce extra non-radiative recombination sites to diminish the efficiency of the solar cell. And so essentially you can optimize the solar cell and upconverter separately in order to create the most efficient device. So how does an upconverter work? Well, most upconverters can be described by a three-level system where we have, again, a valence and a conduction band, but with an intermediate level in between. So first, a lower energy photon is absorbed and excites an electron from the valence band into the intermediate band. A second photon excites it again into the conduction band. And finally, a radiative recombination event across the band gap results in the emission of a photon with a higher energy. If the energy levels are matched up, this higher energy photon can actually be used by the solar cell. So to model how much an upconverter might be able to improve the efficiency of a solar cell, we turn to a detailed balance approach, which was developed decades ago and has been used to calculate the sort of maximum efficiency of an idealized solar cell in the past, based on the fact that the electric current in the solar cell can be approximated as the difference between the amount of photons absorbed by the cell and the amount of photons emitted by the cell. Sort of to update this model to include an upconverter, we simply add a few cells to this detailed balance approach, where the upconverter is modeled as two low bandgap solar cells driving a light-emitting diode into forward bias. So as a sort of basis for comparison, we first start out by just calculating the efficiency of the solar cell on its own. Here I'm plotting the efficiency as a function of both bandgap and concentration, and we can see that for non-concentrated sunlight, we recover basically the curve that Shockley and Kweisser calculated about 50 years ago, which peaks at around 30% for a single junction ideal solar cell. Now, if we add to this ideal solar cell an ideal upconverter, we find that the efficiency is boosted across the board for all of these parameters, for all the range of parameters that I've shown here. In this case, for non-concentrated sunlight, the efficiency is increased from about 30% for a single solar cell to about 44% for the combined device. Interestingly, and sort of actually as we expect, the relative increase in efficiency is largest for large band gaps because more photons are wasted the larger the band gap you have. Another interesting thing that we can get from this model is actually some information about the properties of the ideal upconverter that we might like to design. In this case, this plot shows you for a given band gap of solar cell that you want to work with, what energies of the upconverter would be the best in terms of improving the efficiency by the most. All of these calculations that I've just showed you are for ideal conditions, however. So it's important to consider how a realistic upconverter and a realistic solar cell change this story. Sort of as we expect, if we decrease the amount of light that can be absorbed by the solar cell, the efficiency of the combined device decreases. And as we introduce sort of more non-radiative recombination events into the process, the efficiency decreases as well. But more interestingly, we also consider the fact that an upconverter can only absorb, over a narrow bandwidth of wavelengths. And so in this plot of optimized cell efficiency, here we have cell bandgap on the y-axis and upconverter bandwidth on the x-axis. And you can see at an upconverter bandwidth of 0, that would correspond to the Shockley-Queisser limit. Now, even if we increase the upconverter bandwidth by 100 millivolts or a few hundred millivolts, we can see a very substantial increase in the combined device efficiency of about 5% or even more. So now that we sort of understand how these sort of realistic or realistic-like upconverters would behave, let's consider what upconverters actually exist today. Well, one of the most promising upconverting systems is based on lanthanide upconversion. Here we see nanoparticles of sodium yttrium fluoride that have been doped with the lanthanides erbium and ytterbium. And in fact, these particles are also sensitized with the dye to increase their absorption cross-section. But in essence, we absorb near-infrared light around 800 nanometers and emit light in the green, as you can see in the spectrum on the bottom. Now, if we plug these exact spectral characteristics into the model that I just described and assume various upconversion efficiencies, we can see that with a 100% upconverter operating in this spectral window, we can calculate an improvement in solar cell efficiency of as many as 6%, depending on the solar cell bandgap. Unfortunately, in reality, these particles are only about 1% efficient in terms of their ability to upconvert light. So as you can see, the lowest line, that sort of dark or black line on this plot, corresponds to the no upconversion case as well as this 1% upconversion case. So essentially, there's no enhancement for efficiencies that are as low as they are today. However, if we can boost the efficiency to even 20%, we could get about a 1% improvement in solar cell efficiency. And given that the photovoltaic market is about $100 billion and very steadily growing right now, even a 1% improvement, if it could be done very cheaply, could actually have a big impact. So how can we improve today's upconverters? Well, one way is based on sort of the properties that I discussed in the very outset of this talk, which is that we can actually confine light and concentrate light using these nanoparticles. So if we place our upconverter next to a nanoparticle, the antenna or the nanoparticle can concentrate light into the volume around the upconverter, improve the chances that this upconverter can absorb the light, and it will also work in a reciprocal way where it will boost the amount of light that's emitted by the upconverter. One of the sort of most common geometries that has been tackled for this particular problem is a core shell design. So here we have a spherical upconverting particle that's coated in a small dielectric spacer layer to prevent recombination or quenching, and then finally a small metallic shell, in this case gold, for the simulation. So depending on the geometry and the materials used for this particular structure, we can tune the resonance of the plasmonic resonance of this structure to overlap, for example, in the near-infrared, where this upconverter absorbs most strongly. As you can see, we can achieve intensity enhancements of around 50 to 100 throughout the upconverting particle. But what we want to do is we want to do better than this. We want to have a higher field intensity enhancement, and we also want to be able to do it over a broader range. In general, these core shell designs only operate with sort of a single resonance. So, as you might have guessed, I really like the crescent, and so that's the structure that I'm going to propose as a good way to improve this upconversion process. So if we replace the dielectric core of the crescent with an upconverting core, we should be able to enhance both the absorption and the emission from this upconverting system. If we look at the field enhancement as a function of wavelength throughout this core, we can see that there are multiple resonances that we could make use of. And if we look at the lowest order resonance, in this case, we can see enhancements on the order of at least 100, peaking at around 10,000 near the tips of this structure. So this could significantly improve the absorption qualities of our upconverting system. Beyond absorption, we can also improve the emission. And so for this, we essentially calculate the amount of light that's emitted by an upconverter, both in free space and when it's embedded in the crescent. And when we do that, we find that the enhancement of this emitted power can be up to a factor of a few hundred, depending on which wavelength we're interested in. So to wrap up this second section, I've showed you how upconversion can significantly improve the efficiency of solar cells, but that existing materials really need to be boosted before they become practically relevant. I've also introduced a nanophotonic structure, the nanocrescent, and showed how that could possibly enhance both the absorption and the emission of an upconverting system. But it's easy for me to propose this sort of theoretical structure as a great way to improve upconversion properties or as a constituent of a broadband metamaterial. But what we'd really like to know is, how does that compare to reality? How would this field profile, for example, look if we were actually able to study it at the nanoscale and sort of with a real structure? And that brings me to my final subject, which is a new technique to actually probe these light-matter interactions at the nanoscale and in 3 dimensions. So before I jump into the new technique, I'd like to give sort of this microscopy space some context, and that is to say that people have been interested in looking at light-matter interactions of really small objects for hundreds of years. Back in the 17th century, Van Leeuwenhoek invented essentially the first microscope, and he used a tiny lens, as you can see at the top of this object, which he looked through by holding it up to his eye and placing a sample at the tip of that needle and positioning it with these little screws. Using this really rudimentary but amazingly innovative device, he was actually able to be the first person to visualize a bacteria, as well as a number of other microorganisms. In the few hundred years since then, there have been considerable technological developments. This is actually a microscope that we have in our lab today. But regardless of when a microscope was built or will be built in the future, all conventional optical microscopes are limited in resolution by a fundamental process called diffraction. So to explain this, imagine we have an object on our sample, which could be, for example, a point source of light. Because of the diffraction of light through the objectives and other parts of the optical path in our microscope, this object will look like a blurred spot. And if we have 2 objects in our sample and we bring them closer and closer together, eventually they're going to essentially look like a single object, and so we won't be able to resolve the 2 different things. This sets a fundamental maximum resolution on the microscopes based on these conventional optics to about half the wavelength of light, or about, for this example of a green dot, about 250 nanometers. There have been several methods that have been able to surmount this diffraction limit developed in recent years. One of them, which I'll describe very briefly, is based on near-field interactions of light and matter. In this case, a scattering near-field optical microscope was developed based on a metallized atomic force microscope tip, where they used the tip to both launch and detect propagating surface plasmons on a thin graphene ribbon. In this case, the wavelength of these surface plasmons was 40 times smaller than the wavelength of the incident light. So they were able to beat the diffraction limit by about a factor of 20. In this case, they were able to correlate their experimental signal with sort of the optical landscape right above the graphene sheet. Rather than relying on photons to achieve subwavelength imaging, we can also use electrons. And here we can see a silver prism image in a transmission electron microscope. And in this case, the researchers used a technique called electron energy loss spectroscopy to study the optical properties of this particular nanoscale system, and that's what's shown on the bottom right. It's basically a map of the particular mode of this triangle at the energy given there. But unfortunately, despite all of the progress in sort of subwavelength imaging, most of these techniques are limited to 2-dimensional imaging, so we can only create these 2-dimensional maps. To illustrate with a silly cartoon why it would be so much more useful to have 3-dimensional information, we're going to consider if we wanted to know what this woman was doing, or more particularly what this woman was holding, if we only could look at her shadow. So if we had one source of light and one shadow to look at, we would be able to tell that in her left hand she was holding a banana. If we had a second source of light, we could see now, based on the second shadow at an orthogonal angle, that she's actually holding a pineapple in her other hand. So clearly, imaging from different angles yields additional information. And this basic principle has been used in the medical imaging field, where essentially by taking 2-dimensional X-ray images of your body at different angles, they can then use mathematical algorithms to then reconstruct the 3-dimensional object. And this process is a process called tomography. So tomography allows the reconstruction of a three-dimensional function if we have two-dimensional projections of that function. But sort of back to our sort of nanoscale imaging interest, very recently, a group based in England showed that they could combine spectroscopic electron microscopy with tomography to probe optical properties in 3 dimensions and at the nanoscale. So here they were looking at a silver nanocube in electron energy loss spectroscopy, and by tilting the sample and combining their spectra or their tilt series with tomographic methods, they were able to generate images related to the localized surface plasmon resonances of this particular system. While this was a really beautiful and innovative work, it does have one significant limitation, which is that this particular technique, EELS, indiscriminately probes both radiative and non-radiative properties. So back to our example of an upconverter in a nanophotonic structure, if we wanted to know how much light that upconverter could emit in a particular nanostructure, we would really be interested in the radiative properties of our structure, not both the non-radiative and radiative properties. So the question that we'd like to address is, can we probe just the radiative optical properties with nanoscale spatial and spectral resolution in 3 dimensions? And today I'll show you in this last section how we can use a technique called cathode luminescence and combine cathode luminescence with tomography to achieve this goal. So cathode luminescence is essentially the emission of light upon excitation with an electron. So here we're looking essentially at a schematic of a scanning electron microscope chamber where we have a paraboloid mirror that redirects this cathode luminescence light emission outside of the chamber, and then it can be processed by a spectrometer and CCD. Sort of a simple example to show you how this technique can be used to study nanoscale systems. This is a ridge antenna of about 300 nanometers in length that has been created in a single crystalline gold sample. Now, depending on the wavelength of light that we're interested in, we can use this cathode luminescence signal to map out the different modes of this structure. Another really illustrative example of why cathode luminescence is great for probing the radiative properties of a material specifically, we look to this photonic crystal built into a silicon nitride membrane, where in this particular geometry, the cathode luminescence signal is directly proportional to the radiative local density of optical states in this structure. So with this cathode luminescence map on the lower image, we could actually use that, for example, to know where to place an emitting thing, like an upconverter, such that its emission properties were enhanced the most. In general, the cathode luminescence signal is actually a complicated mixture of different processes, including radiative decay of electromagnetic eigenmodes, as well as material luminescence from electron-hole pair recombination. So we can see how this technique could be really useful for addressing our needs of probing the radiative properties of a system. But of course, we need a system to look at. And so again, I'm going to look at the crescent for this proof of principle experiment. And for the crescent is really ideal for this proof of principle demonstration for 2 reasons. First, it's a 3-dimensional structure. And so it's when we do tomography on this particular structure, it will actually yield interesting information. And in a slide or 2, I'll show you the second reason, which is based on the modes and different radiative processes that this crescent supports. But essentially, we have a dielectric core made out of polystyrene that's around 200 nanometers in diameter, coated asymmetrically with this gold shell. And to make this, we simply disperse polystyrene beads on a substrate and then evaporate metal onto these beads while the sample is rotating at an angle. So this yields really nice uniform crescents that look a lot like sort of our idealized cartoon. We can use a transmission electron microscope to better characterize their 3-dimensional qualities, and by tilting the sample, we can actually see the sort of really 3-dimensional nature of this crescent structure. So here I'm just essentially creating a tilt series where I'm tilting in 2 orthogonal directions. As I mentioned, the other reason why this particular structure is great for our proof of principle demonstration is that the crescent supports many radiative optical transitions. One that I haven't mentioned yet is material luminescence. So most people don't think of metals as great emitters, but it turns out that when you nanostructure gold in particular, because of the inner band transitions that are accessible with light in gold, you can actually get a lot of light out of gold if you pump it. So here we're pumping our gold crescents with a laser at 488 nanometers, and we can see this really broad peak corresponding to these inner band transitions in gold. The other process that I've sort of described in the previous two sections is this plasmonic mode supported by the crescent. In this particular geometry and with these materials, this mode peaks at a wavelength of around 800 nanometers, and we can see, based on the near-field plot, which looks pretty familiar based on the prior two topics, that this mode is characterized by a strong dipolar resonance at the tips of the structure, which lead to a pretty strong field enhancement. So let's look at how we can probe these different properties with cathode luminescence. So here we're going to sweep the beam in a one-dimensional line scan from the base of the crescent up through the center towards the tips. And when we do that, we can see these two particular spectral features. The first one, when the beam is passing through the base of the crescent, when it's going through the thickest portion of gold, we see this material luminescence from these inner band transitions coming out in these lighter colored lines peaking around 600 nanometers. When we sweep the beam up towards the tips of the structure, where that plasmonic mode is supported most strongly, we can see that the photoluminescence peaks again around 800 nanometers. Looked at in a slightly different way, we can really see the sort of spatial and spectral segregation of these two different types of photoluminescent signal in our crescent structure. If we can extend this one-dimensional scan into two dimensions, and here if we plot a CL scan where we raster the beam back and forth in 2 dimensions at a wavelength of 850 nanometers, we can see this strong plasmonic mode supported at the tips of the structure. At a different wavelength, corresponding to the material luminescence, we, as expect, see the signal coming most strongly from the gold shell. As I mentioned, we want to push this into the third dimensions. The plots that I've showed you so far are clearly just two-dimensional plots, but we want to do tomography. We want to be able to reconstruct a three-dimensional function, and that requires us to have two-dimensional projections of the function at different angles. So what we do is we build up a tilt series, and by tilting the crescent and taking these photoluminescence maps in 2 dimensions at each angle, here I'm just showing 3 out of 14 angles that we collected, and by combining these tilt series together using a process called filtered back projection, we can create a 3-dimensional reconstructed image of the photoluminescence signal. So here is the photoluminescence tomogram at 850 nanometers, which just shows you the sort of strong signal localized to the tip region. Looked at in a slightly different way, we can sort of fly through the crescent, and here I'm going to be comparing the reconstructed photoluminescence signal on the right with a TEM reconstruction based on that tilt series that I showed you in the very beginning, where here the darker colors of the TEM reconstruction correspond to regions of higher atomic mass, so that would be the gold. So as we fly through, you can see how at first we can only see the material luminescence in the shell, but when it goes to that center point of the crescent structure, we can see a really strong that resonance, the plasmonic resonance at the tips of the structure. Looked at sort of in a static view, we can sort of chop up our tomogram into slices. And what's most interesting here is that when we compare the experimental photoluminescence slice from the tomogram on the left with our original sort of field profile calculated using a finite difference time domain method, we can see the great correspondence between the experimental and the theoretical predictions. Here I'll just note that the signal that looks like it's coming from the shell of the crescent is actually, like I mentioned, the material luminescence, which isn't taken into account for this particular simulation. That's why they do look slightly different. Of course, photoluminescence, as I've mentioned, is a spectroscopic technique, so we can probe the photoluminescence signal at every point in our 3-dimensional space of our reconstructed tomogram and plot out spectra for each of these voxels, or 3-dimensional pixels. And when we do that, we can see, sort of as we expect, when the voxels are located in the base of this crescent structure, the signal peaks at shorter wavelengths corresponding to the material luminescence, and then for voxels closer to the tips, we see the strong plasmonic resonance. We can actually correlate that to real physical quantities. As I've mentioned before, the material luminescence can be probed through photoluminescence measurements, but more interestingly, we can actually calculate the radiative local density of optical states in these particular nanoscale voxels, and they actually correlate quite well with the signal that we get in our 3-dimensional tomograms. So to sort of pull this all together, we can plot out three-dimensional tomograms as we span the different wavelengths probed in this technique. So starting out here at a wavelength of around 477 nanometers, you can barely see it, but it turns out that there's actually some small signal coming from the polystyrene bead in the center of the tomogram, which is a pretty interesting finding. But at these wavelengths that around 500 to 700 nanometers, we see that the signal is primarily coming from the metallic shell, as I've mentioned a number of times, but then that changes, and as the wavelength gets closer to the near infrared, we start to excite that plasmatic mode at the tips. Looked at in sort of a more static series of pictures, we can really see the evolution of this cathodoluminescent signal as a function of wavelength. So to wrap up this third and final section, I've sort of introduced you to a new technique called cathodoluminescence tomography that can be used to image light-matter interactions in 3 dimensions. And I've showed you that the signal can actually be correlated with material luminescence and the radiative local density of states for these various transitions. So to conclude this talk, as well as the 5 years that I've spent here at Stanford, I've showed you that through rational control of nanoscale light-matter interactions, we can do 3 pretty amazing things. We can design metamaterials that operate over a broad spectral range. We can enhance solar cells by utilizing sub-bandgap photons. And we can even probe the optical properties of a nanoscale system in 3 dimensions. So, of course, I have to acknowledge all of the people that contributed to this work. First, I'll mention that my direct collaborators, Eitzel and Hadise, have been instrumental in a lot of the projects that I've worked on. Justin and I worked closely on the modeling of the upconversion process. Diane and I have been working quite closely recently on some experimental realizations of the upconversion enhancement project, as well as some making some of these crescent-based metamaterials. Of course, the entire dionne group, you've supported me in ways that I can't even begin to elaborate on. Ben, Toon, and Albert at the Foam Institute Almolf were our very close collaborators on this CL tomography project. They have really been instrumental in developing the cathodoluminescence process or technique in 2 dimensions, and so we were very lucky to be able to join them in Amsterdam for a few weeks to do those experiments. And I worked very closely with Ben and Toon on that project. Of course, I also want to thank my committee members, Shanhui, Mark, Alberto, and Mike. I really appreciate you taking the time to be here. I've also had the pleasure of taking classes from each and every one of you, and so that's been a really nice experience while I've been here. And that leaves me with Jen. Of course, I have to poke a little fun at her because I knew that she'd be doing the same in my intro. So this is Jen on Halloween about a year ago, dressed up as Mia Wallace from Pulp Fiction. But to sort of describe the last 5 years that I've spent here, I sort of want to give you a little sort of pictorial tour. It'll be very brief, but I think it'll be fun. So I've been with Jen for, as she mentioned, at least 5 years now. John and I basically were her first students, along with Amr and Hadise. And back in the day, we used to sit outside of her office, essentially, in the lobby where our simulation computers were, because our labs and our offices looked like this. We were pretty eager to get into the lab, and so we couldn't resist picking up whatever we could find and getting our hands dirty, which happened to be some copper pipes and 2x4s. We also had a lot of free time on our hands, so we did a lot of fun stuff like roller skating, disco roller skating, where you can see Jen here fulfilling her lifelong dream of being a professional ice skater. Eventually, our labs were completed, and we were able to use them, and we got pretty serious. And eventually, we even had our optics lab up and running, and we did really safe optics experiments. But in all seriousness, because of Jen's sort of amazing leadership, we have been able to get a lot of really good science done, and she's been recognized for doing such. And in case you couldn't tell, that's Jen standing right behind Barack Obama after she was awarded her Presidential Early Career Award. So I thought I'd just point that out. But all this, Jen, is just to say thank you. This is unusual for a thesis defense, but I'm a pretty emotional person. The last 5 years have been really incredible, and I really appreciate everything that you've done. you're obviously one of the smartest people I know, but what really sets you apart is that you go into every situation with like 110% effort. Sorry, it's embarrassing. Anyways, I know 110% is impossible, but that's sort of what defines you. You do things that seem impossible, including nursing your baby while giving a teleconference presentation. Anyways, you're totally incredible, and I think, I just thank you for taking me in from day one and really supporting me. And to the rest of the group, you guys are obviously all amazing scientists, but what I'm going to remember after I leave here is everything else that we've done. So, our deep philosophical discussions, or our gym sessions, or swimming with Diane, or whatever it is, that's the stuff that I'm going to remember most. To my family, thank you, Mom and Papa and Scott, for coming. This is really special to have you here during this time. I'm sorry that Anu couldn't be here, but I'm excited and looking forward to spending more time with you guys soon. And finally, to Olivia, you are my rock. 3 years ago, our paths crossed, and I don't think that I could have chosen a better timing if I had tried. So thank you for all the support that you've shown me over the last couple of years. And with that bombshell, I will bring back up my concluding slides so that you can ask me any questions.